It's going to be a section on 14.2. I actually want to start, though, with one of the problems you had in your previous assignment. This is problem 14 from the worksheet that we went over. I'm going to take tan squared on top, and I know that tan squared is the same as secant squared minus 1. We have an identity that says that tan squared theta plus 1 is secant squared. So I can just subtract the 1 from both sides, and that tells me that tan squared is really secant squared minus 1. So this becomes this, and it's over secant theta plus 1 and then plus 1 here. Well, this on top, this is a difference of squares. It can factor into secant theta plus 1 and secant theta minus 1 over secant theta plus 1 with a plus 1 on the end. This plus 1, secant theta plus 1, cancels with the secant theta plus 1. So you have secant theta minus 1 plus 1, which is just secant theta. Okay, I'm going to go through a ton of examples. I'm going to do them very quickly, because remember, you can always pause and rewind. What we're doing now is not just simplifying, but verifying, and we want to try and make one side look like the other. It's nice because you have a goal that you're shooting for. You're not just blindly trying to get an answer of 1 or cotangent or something, but actually know that I want to make this look like this, or other way around, make this look like this. Either way. You can even make them meet in the middle if you want. One thing to be aware of is even though we have equations now, even though we have this equals sign here, you can't do something to both sides of an equation. Like I can't multiply both sides by 1 minus cosine theta. Excuse me. I'm not allowed to do something to both sides of an equation because every once in a while you'll be multiplying by 0 and not know it, or there's always the potential of multiplying by 0 or dividing by 0. So you can still only play with one side at a time. Now I'll show two ways to do this first problem. I look at this and I think I really wish that was 1 minus cosine squared, because 1 minus cosine squared is sine squared, and that would be useful to me. But I don't have 1 minus cosine squared, so I want to try and make a 1 minus cosine squared. So what I do is I multiply the top and the bottom by 1 plus cosine. And when I do 1 plus cosine, on the bottom, when this foils out, it becomes a difference of squares, 1 minus cosine squared theta. And on top, I'm just going to leave it 1 plus cosine theta sine squared theta. Well, 1 minus cosine squared, I know on the bottom, 1 minus cosine squared is actually just sine squared. So I have 1 plus cosine theta times sine squared theta over sine squared theta. These now cancel, and I get 1 plus the cosine of theta. This is the same as this, so I've done it correctly. That's one option for how to handle that. Another option, almost all these problems can be done in multiple ways. Another option is to just take sine squared and split it up into 1 minus cosine squared. I know sine squared plus cosine squared is 1, so 1 minus cosine squared gives me sine squared. I now have this on the left side. I can't cancel those cosines, and I can't cancel those 1s. Nothing right now can cancel because this square kind of ruins things, and these two minuses kind of ruin things. But the top of this can factor. It's a difference of squares. So the top becomes 1 plus cosine, 1 minus cosine. The bottom is still just 1 minus cosine. These cancel, and I'm left with 1 plus cosine. Okay, next one. This problem down here has, it goes from having 2 terms to having 1 term. Whenever that happens, whenever you go from 2 terms to just 1 term, you have a very good indicator, a very good indicator you're either going to factor or use a Pythag identity, and often both. Could be both, could be either. I am going to play with the left side because it just makes more sense to me with the squares and the minuses that I'm going to look for a Pythag identity somewhere. There's no Pythagorean identity that involves cotangent and cosine, but cotangent I know is cosine over sine. So I'll get a common denominator. Because I have fractions, I'll get common denominators, so I multiply by sine squared over sine squared. And that gives me cosine squared. On top I have cosine squared theta minus cosine squared theta sine squared theta over sine squared. And now I'm going to factor. On top, I have a cosine squareds in common with both of these. So I pull out the cosine squared, and I'm left with 1 minus sine squared. I know that 1 minus sine squared, right here, I know that 1 minus sine squared is actually cosine squared. So I have cosine squared theta, so I'm writing pretty poorly because I'm trying to write so fast, over sine squared. And one of these cosine squareds over sine squares is cotangent squared. This right here becomes cotan squared cosine squared. And there, I got what I wanted. Great, keep moving. Cotangent, cosecant. The more stuff you have to work with, the better. So I'm going to start on the left side of this problem also, just because I've got more stuff to play with. I know that cotangent is cosine over sine, and cosecant is 1 over sine. One thing you'll start to realize is that things on bottoms can cancel, or things on tops can cancel. You can cancel things that are in the same spot, because what you end up doing is just multiplying by the reciprocal. You do cosine sine times sine over 1, and this cancels with this, so your answer is just cosine, and that's what I wanted. That was a pretty simple problem. Now this problem here is going to relate pretty closely to this problem here. Let's see, I think I'll go with purple. Cotangent is, I kind of, yeah, I'm just going to make this cosine over sine and see what happens. I'll get a common denominator. I'm pretty sure this will work out okay. The common denominator is cosine sine. So this needs a sine on top and a sine on bottom. This needs a cosine on top and a cosine on the bottom. And that leaves me with cosine squared plus sine squared. Beautiful. Over cosine sine. Well, cosine squared plus sine squared is 1. So it's 1 over cosine sine. And 1 over cosine sine is secant cosecant. And that's where I wanted to end. It's not the only way to do this. You could try and take cotangent, make it 1 over tangent, and then multiply by tangent over tangent, or something like that. You could play with secant and cosecant, but I think starting with stuff that has addition makes things easier. Okay, next problem. Sine times cosecant is just 1. You should really look for things like this, because it's sine times 1 over sine, and sine times 1 over sine is 1. So it's cosecant squared. I'm sorry, I don't want to worry about the left side. I want to play with the right side. So it just becomes cotan squared plus 1, and cotan squared plus 1 is cosecant squared. That's one of your Pythagorean identities. Great, moving right along. Next one. This is a problem that's kind of silly, but I think very instructive. I always do this problem at this point of the year. Cotangent is cosine over sine. It's very important you get on top of cosine, or cotangent being cosine over sine, and tangent being sine over cosine. So tangent is sine over cosine. Secant is 1 over cosine. Cosecant is 1 over sine. You want to be able to do those very, very quickly without having to look anything up. Well, a cosine on top and bottom can cancel, a sine on top and bottom can cancel, a cosine on top and bottom can cancel, and a sine on top and bottom can cancel, and this just equals 1. Just comes out to 1. The point I'm trying to make, which you should see, cotan times tan is 1, cosine times secant is 1, sine times cosecant also 1. Those are 3 things you should be looking for. We've got lots more to do, but they're going to get a bit more complicated. Like I said, I'm trying to go fast. This isn't too long, and you can always pause and watch problems as we go. There's 2 tricks I'm going to do on this problem. One of them is whenever you have a 2 times something, you can make it 2 somethings. 2 sine squared x is really sine squared x plus sine squared x minus 1. Take the 2 and split it up into 2 separate things being added together. This became this. Now sine squared x minus 1, well, I know that cosine squared and sine squared is 1, which means that Sine squared minus 1 is negative cosine squared. I subtracted this from both sides, and I subtracted this from both sides. So this becomes a negative cosine squared. So it's sine squared x minus cosine squared x. And I could play with that a little bit, but I think I'm going to leave that the way that it is and play with the other side now. You're free to play with the two sides independently. That's not an issue. This is a difference of squares. Sine to the fourth and cosine to the fourth are both perfect squares, so I can think about it as a difference of squares. Sine squared x minus cosine squared x, and sine squared x plus cosine squared x. Oh, but sine squared and cosine squared is just 1. Which is just this. I got these two things to meet in the middle. I made this side and this side meet in the middle, and since I was able to do that, I know they're actually equal to each other. What I could do now is just take one side and finish it over on the other side. Like I could take this step and write it over here. I could do this times 1. And I know that 1 is really just sine squared plus cosine squared. And you're not used to taking things that are small and making them bigger. In all of math, you've always simplified. And now you do the opposite sometimes. You take things that are simple and you blow them up a little bit. And once you blow them up, then you can start foiling and expanding and doing things. We end up with sine to the fourth minus cosine to the fourth. And that's where we wanted to end. But getting to meet in the middle is just fine. If you meet in the middle and stop, I'm okay with that. Okay, I'm going to do the same trick here. Having a 2 cosine squared is really having 2 individual cosine squareds. I have to make them both negative. Now when I do this in class, I actually do this one wrong the first time. Not always intentionally, sometimes I just do that naturally. But I kind of want to show how to do this right just for the sake of saving some time. 1 minus cosine squared, this right here. 1 minus cosine squared is just sine squared. And I have this single term with a minus on top. So what I'm going to do is split it up because I want to get 2 terms out of this. I'm going to split it up. I have sine squared theta over sine cosine, and cosine squared theta over sine cosine. And now a sine here can cancel a sine here, and a cosine here can cancel a cosine here, and I'm left with sine over cosine minus cosine over sine, which is tangent minus cotangent. Again, I apologize for the messy writing. Sometimes in the past I've just not dealt with thetas because they can just make things messier. But there they are. I got my tangent minus cotangent. Okay, I think we just did this one. Is that right? Yeah, we just did that one. I copied it over to save space, but I don't need to do that anymore. So I'm down to this one. I'm actually not totally sure how I want to handle this one. I don't know if I want to do the left side or the right side. I think I'm going to play with the left side first, just because it seems to lead somewhere. Let's see, if I FOIL this, man, this is written really big, I'm going to write it smaller. If I FOIL this, I'll get 1 minus cosine to the fourth of x. I don't want cosines, I want sines. So maybe I'll do this. Here's kind of a weird trick. I know that 1 minus cosine squared is sine squared. Yeah, I think this is going to work. 1 plus cosine squared doesn't tell me anything. But I can take that cosine squared and write it as a 1 minus sine squared. I know cosine squared is 1 minus sine squared. So I can take this and take this cosine and change it into a 1 minus sine squared. I'll simplify, so now I have sine squared of x times 2 minus sine squared of x. Ha! And that's going to give me 2 sine squared minus sine to the fourth. Just what I wanted. Beautiful. So this problem, I had to stop and look and think at for a while. I had a bunch of cosines, and I really wanted to make them sines, because everything I needed had to come out to a sine. So instead of foiling just would have given me a cosine to the fourth, and that doesn't really help me a ton. I figured this is really just a sine squared, so I should take this and also find some way to make it a sine squared, and that's 1 minus sine squared. Then I had a whole bunch of sines everywhere and just kind of hoped for the best. I could probably have played with this side also, like made this a sine squared plus a sine squared minus a sine squared times a sine squared. Or I should just factor out a sine squared from everything, really. That's what I should do. Yeah, that looks better. Then take those sines and make them cosines. And that gives me 1 minus cosine squared times 1 plus cosine squared. The negative has to distribute to those. And that's what I would have wanted. So I can do that from either side. I believe that takes care of them all. Hope you found that helpful. Thank you.